Hello and welcome to part 2 of lecture 17. In this part, we're going to talk about how we can take a polynomial and apply it to an operator to get a new operator. Okay. So first of all, let's make an observation that if we take a linear operator, then it makes sense that we can also talk about t composed with t. That is also going to be an element of the set of all linear maps from V to itself. Okay, so um, we can always take a map, a linear operator, and compose it and get another linear operator. Okay, so that allows us to introduce the following definition. So if we take any linear operator, then we're going to let t to the m mean that we're taking the operator and we're composing it with itself m times. Okay, so there's m times here. So the idea here is if you're looking at, say, t to the 5, and you're looking at what happens to a vector when you stick it in, you first stick it into t, you get an output. Then you stick it back into t again, and then you stick it back into t again. And you do that 5 times, or whatever the value of m is. We're going to define t to the 0 to be the identity operator. And if t is an invertible operator, then by t to the negative m, what we mean is we mean the inverse of t composed with itself m times. Okay, and the nice thing about this notation is it kind of obeys our regular exponent notation. So what I mean by that is when we write t to the power of n plus m, that's the same thing as writing Tn times Tm. So remember, this means composition of operators. And same thing over on this side. If we take an operator, raise it to the power of n, and then raise that operator to the power of m, that's the same thing as taking the operator t and raising it to the power of n times m. Okay, so let me just kind of explain here what we can do with this. Suppose that we have an operator in, we have a linear operator. Okay, so we have a vector space. T is a linear map from V to itself. And I give you any polynomial, okay, where the coefficients are in the field. Then we can take this linear operator and plug it. In some sense, we're going to plug it into our polynomial. And what we get is an operator of the form A0 times the identity plus A1 times the operator t all the way up to am times t to the m. Okay, and what you want to observe is that this is an element of L to the v. Okay, so you kind of want to, we'll maybe do an example, we're going to be doing an example in a second, but what you want to think of is normally t has the property that I take something in big V and I can plug it in and I get something back in V. So now you want to think of this giant thing as a function. Okay, so let's maybe do an example here. If I were to say if I were to take t in LV, and if I were to take the polynomial t plus 5, that should be 5z squared, then when I talk about pt, I mean the operator 2 times the identity operator plus 5 times t squared. Okay, and let's see if I left myself enough room here. So what you want to think about is I can now take an element inside of V and I can say, well, where does this get sent to? Well, this gets sent to, well, this should be the identity operator. This gets sent to 2iv plus 5t squared v. All right, so you can think about this as 2 times the vector v plus 5 times the vector that I get by plugging v into t and then plugging it back into t and then taking a scalar multiple. Okay, so hopefully this helps. In the next part, I was actually going to do a bit more of a detailed example to kind of help you out understand this idea of applying a polynomial to an operator.